this video is going to look at your geometric series. In the previous videos, we covered sequences and we have had a look at your arithmetic series. So now we're going to start with the geometric series. Okay, so I'm just going to give you the formulas that we use for calculating the sum of a geometric series, and then we're going to derive them. After that, we'll look at examples. Okay, so previously we used this first two to calculate the sum for an arithmetic series. Okay, so now we're going to look at these two. Okay, so there's two sides of the same coin, you can say. And then this last one will be covered in a later on video. So let's start with this one. So I'm just going to prove this one and show you how you would obtain this one. And then we go and have a look at examples. So, say you are required to prove that for any geometric series, you can find its sum using this equation. How would you go about it? So the first step that you're going to do is to say that Sn is actually a sum of the terms in a series or in a sequence. Okay, so this would be something like this, to Tn, or to Tn minus 1 plus Tn. So this is the term before the last term. Okay, when this is so, we can then convert this to say Sn is equal to A plus AR plus AR squared plus I'm just going to put the last term for now here, ARn minus 1. This would be n minus 2. Okay, so once we have this, okay, addition sign here. So once we have this, what we then do, we're going to multiply this whole thing by r. So you're going to have r Sn is equal to AR plus AR squared for this one, plus AR cubed for this one, plus, so here you'd have AR to the exponent n. Okay, let me just include for this one. Okay, so it would be ARn, so this one would be ARn minus 1 plus ARn. So for how we got to ARn is like this. Let me just show for this 2. For this one, you have ARn minus 2, which is equal to Tn minus 1. Then you multiply it by r. So multiplied by r, this is the same as r to the exponent 1, right? So you have ARn minus 2 plus 1 because of the multiplication sign. This results in ARn minus 1. So this is how we could get this one. So how we get this one is we have ARn minus 1 multiplied by r, which is r to the exponent 1. Then it's ARn minus 1 plus 1. Okay, and this is AR to the exponent n. So this is for the last term. So once we have this, I'm just going to rewrite this in a different way so that you have a good view of it. So I'm just going to write and start with Rsn. So we'll say Rsn is equal to, I'm just going to start here, AR plus AR squared plus AR cubed plus ARn minus 1 plus ARn. Okay, and then I'm going to rewrite this one. I'll say Sn is equal to A plus AR plus AR squared plus ARn minus 1. Okay, so I'm just writing this out so that our next step is easy to see. So this is how we're going to proceed. Let me just write this down here. I'll erase. So we're going to say if this is term number 2. So if this is term number 2 and this is term number 1, 1, 2. Okay, we're going to say term number 2 minus term number 1. In other words, RSN minus SN. Okay, so by doing this, you have RSN minus SN is equal to, then you substitute also this part. So here you'll have a 0. So it's going to be 0 plus u. You know that 0 does not affect the sum, right? And this is actually so that our computation looks simple. So it will be 0 minus a, which would be negative a. Then here you'll have AR minus AR. So this would then be equal to 0. You have AR squared minus AR squared. This also cancels. And then you can see that if you were to have AR cubed here, this would cancel with a term here. And every term would cancel, okay, up until you get to this one. This one would cancel with the last term for Sn. Then you are left with this one as AR minus, or plus, actually plus 0 on this side. So you'd be left with plus AR to the exponent n. Okay, so what I'm going to do, I'm just going to interchange these ones and also take out a common factor. So here we have a common factor which is Sn. So we take it out, we have Sn into r minus 1 is equal to, and this side, you take this to the front, you have AR n minus 1 minus a. Okay, this side you also have a common factor which you can take out, which would be a into Rn minus 1. Okay, and then this side you can actually divide by r minus 1 so that you are left with Sn. So you can say, okay, Sn divided by r minus 1. And by so doing, you just proven that the sum of a geometric series can be calculated using this formula. So Sn is equal to a into r to the exponent n minus 1 divided by r minus 1, which is the same as this. Okay, so as you can see, this is only this part of the this expression or this equation. So how a person would get to this one, they would take a different approach to this. So instead of saying r Sn minus Sn, you'd say Sn minus r Sn. Okay, and that way you'd have Sn as a common factor, 1 minus r. And then you can see that when you divide by this, it gives you this at the bottom. Okay, let us now go and have a look at examples. Okay, so here is the first example. It says find the sum to 10 terms of this series. So you have 2 plus 6 plus 18 plus so on. Okay, so here what we're going to do, we're going to employ the Sn formula. So the choice of formula that you use, you're going to actually look at something. So you look at r. If r is greater than 1, you use the first one. If r is less than 1, you use the second one. So this makes it easy for you to do the calculation. Okay, so let's use the Sn formula. Actually, let us look at r. What's our r here? R is equal to 6 over 2, which is 3. Okay, so if it's 3, it's positive, it's greater than 1, we can use this one. Okay, what is our r? Our a. Our a is 2. Then what is our n? Our n is 10 because they want the sum to 10 terms. Okay, we can now start and say our formula is a into Rn minus 1 all over r minus 1. So S10 will give you a is 2, r is 3 multiply to the exponent 10 minus 1, r minus 1, which is 3 minus 1. And then this you can just use your calculator. You'll find your answer to be 59,048. So this is the sum to 10 terms of this series. Okay, I'd like you to try this out using the second equation and comment down below on what answer do you get. Let's go to the second example. Okay, so here's our second example. It says given this series, which is 324 plus 108 plus 36 plus etc. The first question asks, how many terms of the series will add up to 13,120 over 27? Okay, so how many terms will add up to this? So what they're essentially asking is how many terms to get to the sum. So the sum that we are interested in is 13,120 over 27. Okay, so how many terms will add up to this? So we're going to start out by determining what our R is before we can choose which formula we decide to use. So you'll say, okay, R is 108 all over 324, which is equal to how much? It's equal to 1 over 3. So if it's 1 over 3, which equation is suitable? So the second one is suitable because R is less than 1. And also, what's our A? A is equal to 324. N is what we are solving for. Okay? So we can say, okay, Sn, which is equal to this, is equal to that precious formula of ours. Okay, so what we're going to do now, we're just going to substitute. Let me just make some space here. So this is 1 over 3, okay, and 324. So this number over 27 is equal to 324, 1 minus 1 over 3 to the exponent n is equal to 1 minus 1 over 3. Okay, so we are simply going to be doing manipulation here. Okay, so what I would do here is I would say 324 divided by 1 minus 1 over 3, which would give me 486 multiplied by 1 minus 1 over 3 to the exponent n. So what this simply did, it took out this bracket. Okay, then I divide by 486 and divide 486. Okay, so what I then have is 1 minus 1 over 3 to the exponent n is equal to 6,560 minus, divided by 6,561. After this, I'm just going to transpose this. Let me erase. So I've just rewritten this here. So what I would then do is I would transpose. I would take this to this side and take this to this side. So I want to make this positive without having to divide by a negative 1. So I'd have 1 minus 6560 over 6561 is equal to 1 over 3 to the exponent n. So once you have this, you'll have that this is 1 over 6561, which is equal to 1 over 3 to the exponent n. And this is the same as 3 to the exponent 8. Okay, so we have the following this side. So we have 1 over 3 to the exponent 8 is equal to 1 over 3 to the exponent n. Then from here you can then say n is equal to 8. The bases are the same, you can drop the exponents. So we have just calculated the number of terms that can add up to this number. Let us go to the second question. So the question says, determine the least number of terms for which the sum of the series will be greater than 485. So interpreting this, the least number of terms of which the sum of the series will be greater than 485. So we have now interpreted what they want us to do, and then we can just input and substitute. So we have a 1 minus Rn over 1 minus R is greater than 485. Our a is 324. 1 minus 1 over 3 to the exponent n over 1 minus 1 over 3 greater than 485. This still gives us 486 times 1 minus 1 over 3 to the exponent n greater than 485. Then we divide both sides by 486. We are left with 1 minus 1 over 3 to the exponent n is equal to, is greater than. Should not change this into an equal to sign. Okay, so here I'm going to transpose this one to this side. So I'll be left with minus 1 over 3 to the exponent n greater than 486 minus 1. Then we have minus 1 over 3 to the exponent n is greater than. So this you do with your calculator, and then so you're going to get let me erase, minus 1 over 486. So because we have a negative here, I want to get rid of it. This is what I'm going to do. I'm going to divide by a negative 1. Divide by negative 1. So we'll be left with 1 over 3. 1 over 3 to the exponent n is less than 1 over 486. So the reason why this changes is because you have a negative here. You are dividing by a negative. If you were multiplying by a negative, it would also change. So now we're going to solve for n. And to solve for this one, this is what I'm going to do. So this will be different from how we've been doing it. I'm going to say n is less than the log of 1 over 486 with a base of 1 over 3. Okay? And then you can input this into your calculator. So this is actually the same as log 1 over 486 over log 1 over 3. Okay? So this is actually the same. So you introduce a log this side and a log this side, then this drops down, then you divide by the log that is this side. And then you get n less than 5,63. Okay? Another reason why it's a log here, it's because this number, you can't have it as 3 to the exponent something. It's impossible. Unless if it's a decimal. So you have less than 5.63. So what this means is that for you to get greater than 485, you need n is equal to 6 or more. Okay? N equal to 6 or more. Or at least 6 terms. Because remember also, n has to be an integer. Let's go to the third question. Okay, so now on to the third example. Here's our series, x plus x squared plus x cubed plus so on. So you are asked to find the sum to 20 terms, okay? So here, what you can soon realize is that you're given variables. In other words, you wouldn't know if your r is positive, or is greater than 1 or it's less than 1. So what I would do is I would use this first formula, okay? So our a is x, our r is x squared divided by x, which gives us x, and then our n is 20 because it's a sum to 20 terms. Okay, so now that we have all this information, we can calculate the sum to 20 terms. So we have a Rn minus 1 all over R minus 1. Then we say S20 is equal to a, which is x, into x to the exponent 20 minus 1 all over what's our R? It's x minus 1. Okay, so a person can want to multiply further, but this is the simplified version. So this would be your sum to 20 terms again. So this is how you find the sum to 20 terms of the series, which is just variables. So I'm going to stop here for this video. The next video will look at example number 4 and example number 5, and then we're going to start on the sum to infinity, how it was derived, and look at examples.